Modern AI systems are built on decision-making, constantly trying to find the most efficient path through massive constraints, like logistics routing or hospital scheduling. We call this an optimization problem, the mathematical task of finding the single best solution according to a strict evaluation metric, pulled from an ocean of possibilities. The classic benchmark is the traveling salesman problem, where an algorithm must find the shortest possible route between a set of cities. At 4 cities, it is trivial, but as you add just a few more, the number of potential routes explodes factorially. The traditional approach to solving this is systematic or exhaustive search. This explores the entire solution space, examining every single configuration one by one. Because systematic search checks everything, it guarantees you will find the global optimal solution. But for complex combinatorial issues, known as NP-hard problems, the math paralyzes the machine. The number of possibilities rapidly exceeds the number of atoms in the universe. The ultimate constraint on artificial intelligence optimization is time. Waiting to find the exact perfect answer is computationally impossible before the universe ends. To bypass this computational bottleneck, computer scientists use a different approach: heuristics. A heuristic is a search method designed with a deliberate compromise. Instead of demanding mathematical perfection, it uses domain-specific knowledge to seek out a near-optimal solution, something that is good enough, at a reasonable computational cost. Where systematic search must process the entire solution space, local heuristic searches focus their energy on exploring a highly localized subset of that space. By limiting its view, the algorithm sacrifices absolute certainty. It cannot guarantee that the final answer it produces is the true optimal solution. Real-world optimization ignores perfection in favor of pragmatism. The goal is engineering a system smart enough to find the best possible answer before the clock runs out. To see exactly how these systems trade accuracy for speed, we need to build a local search algorithm from scratch. We will use a classic Boolean logic puzzle called the max-sat problem. The objective here is simple: maximize the number of satisfied true or false clauses in a specific formula. First, we need representation. The machine needs to know how candidate solutions are encoded. For max-sat, we use a binary vector, like this 10-digit string of ones and zeros, where each bit maps directly to a variable being true or false. Second is initialization. The algorithm needs a starting line. We generate a candidate solution, often completely at random, to ensure we are dropping our search into a diverse area of the problem space. Third is the evaluation function, our objective scoring metric. For max-sat, the system simply counts the total number of clauses that our current string successfully satisfies. Fourth is the neighborhood relation, or move operators. The algorithm needs a defined way to explore nearby options. If we flip a single bit in our sequence, we generate a brand new, slightly modified candidate known as a neighbor. Finally, we apply the search process. This is the overarching strategy the algorithm follows to iteratively evaluate neighbors, decide which moves to make, and keep improving its score. Together, these 5 components translate an abstract logical problem into a traversable mathematical landscape. The most common search process used to navigate this landscape is an algorithm known as hill climbing. We can track its exact path using a numerical optimization problem, aiming to maximize a specific function defined as negative x squared minus y minus 2 squared plus 4. Starting at coordinate 1, 1, the algorithm evaluates immediate neighbors. The neighbor at 0, 2 yields a higher value, so it moves there. In the next iteration, it discovers no adjacent coordinates provide a higher value. With no upward moves available, the algorithm halts the search. The numbers prove the algorithm successfully climbed a peak. But that raises a critical question. Did it climb the highest peak on the map? Often the answer is no. This algorithm has fallen into the local optimum trap. It found a solution that is strictly better than all the immediate coordinates in its surrounding neighborhood, but it is not the global best. Standard hill climbing only accepts improving moves. It has no mechanism to temporarily accept a lower score, which means it cannot step down into a valley to reach the base of a higher mountain. There are variations to how it climbs. First improvement evaluates neighbors one by one and jumps at the very first better score it sees. It is computationally fast, but effectively blind to the broader landscape. Best improvement, or steepest descent, forces the machine to evaluate every single neighbor before moving. This guarantees it always takes the path of largest improvement, though at a much higher computational cost. Yet regardless of how they analyze the slopes, both methods inevitably get stuck. By strictly refusing to ever accept a worse score, hill climbing guarantees its own failure on complex, multi-peaked datasets. Escaping these dead ends requires a higher level of control, introduced through metaheuristics. These are overarching algorithmic strategies designed specifically to guide the search process out of local optima. Metaheuristics operate entirely around balancing a critical tension within the system: exploration versus exploitation. This chart visualizes the two opposing forces. Exploration searches broadly across new areas. Exploitation focuses on intensely refining known good areas. Effective search requires a phase shift: high exploration at the beginning, shifting dominance to high exploitation near the end. To find the absolute best answer, we must force the machine to cast a wide net early on, before we allow it to aggressively optimize a specific target. The exact mechanism engineers use to enforce this balance is called the move acceptance protocol. Unlike basic hill climbing, a metaheuristic move acceptance protocol is programmed to deliberately accept non-improving, or worse, solutions. This diagram shows the taxonomy of how algorithms decide when to take a step backward. The logic branches into two main paths: stochastic methods relying on randomized probabilities to accept worse scores, or non-stochastic methods following fixed mathematical thresholds. Taking this temporary hit in performance gives the algorithm the freedom to walk down off a local peak, cross flat topographical plateaus, and eventually scale the true global optimum. This architecture is a universal framework. As seen in this visualization of a one-dimensional bin packing problem, the exact same high-level rules can control completely different problem domains. By engineering imperfection into the rules, requiring the machine to move backward to eventually move forward, a metaheuristic search finds the global peak that a direct ascent would always miss.